Good evening. My name is Gabriele Guerrini, and I'm an assistant professor with the University of Pavia in Italy. Today, I will start with a series of seminars about the evaluation of the seismic performance and the mitigation of the vulnerability of masonry buildings. And in particular, I will give you an overview of the framework of the Eurocode 8 Part 3 about this seismic vulnerability assessment procedure and possible mitigation techniques for existing masonry buildings. Now, the framework in the Eurocode 8 basically comprises four parts. First of all, we need to know the building that we are considering, that we are assessing, and we need to know its geometry, details, materials. So this is the first part of the assessment procedure, knowing what we are talking about. Then we need to analyze the building in its current state to understand if its performance is acceptable or if we need to improve it. And typically for masonry buildings, we have two levels of analysis. One related to local mechanisms and one related to the global behavior of the building. Now, usually we perform these two levels of analysis separately. In reality, a wall responding out of plane in a local mechanism is the same wall also behaving, also resisting in its own plane in the global building behavior. So this distinction between local and global analysis is something that is very useful for our tools. But in reality, we may also use models that combine the two aspects together, because in reality, the two levels of analysis are actually interacting with each other. Finally, once we know if the performance of the building is acceptable or not, we may or may not design retrofit interventions. And again, we need to address the possible issues related to local and global behavior. And then we need to repeat our analysis to ensure that with our improvements, we are actually now meeting the requirements, the performance requirements that the code is asking for our structure. So let's start from the first ingredient of the framework, that is the knowledge of the building that we are analyzing. Now, there is a useful table in Eurocode 8, it's table 3.1. When I say Eurocode 8 for existing buildings, I'm always referring to Eurocode 8 Part 3. And this table basically defines different levels of knowledge. We have three levels of knowledge, and it allows us to determine in which of this level we are with the knowledge that we have about our building. The first part of this knowledge is related to geometry. And to determine the geometry of the building, we can make use of outline construction drawings if they are available, if we can find them. For historical buildings, this may not be so easy. For more modern buildings, instead, it's more likely that we can find them. Then we may have to carry out some surveys on the field. If we have good construction drawings, a visual survey may be enough just to confirm that the drawings correspond to the reality, or to adjust where we have some inconsistencies. But in some cases, especially if we don't have any drawing available, we may have to carry out a full survey of the building. Then we need to investigate the details, the construction details of the building. In the most unlikely case, we may have to carry out a simulated design if we don't have any information. But in some cases, we may be able to find some detailed construction drawings where these construction details are shown. In any case, we also have to go on site again and perform some inspections, which can be more or less limited, extended, or comprehensive, depending on what knowledge level we want to reach, and depending also on the available material in terms of construction drawings that we have found. Then we need to characterize the material of our building. Again, we may need to refer to some default values, but we may also be more lucky and have sources such as original design documentation or original material testing results. And we may be able to refer to these values. In any case, it's also better to perform some on-site testing. And again, this test can be more or less extended, going from limited to comprehensive, depending on the amount of element that we are investigating, again, to confirm the choices or the assumptions that we are making. At this point, we can define our knowledge level, depending again on the combination of available documentation, of on-site inspection and testing that we have carried out. And we have these three levels of knowledge: KL1, KL2, and KL3. Each knowledge level is associated with possible analysis methods that can be adopted for the global analysis of the building. If we are in the less favorable case of knowledge level KL1, where we have less information, we can only carry out elastic analysis that are usually more conservative. We don't have, in that case, enough information to build a nonlinear model to carry out such an analysis. So in that case, we need to go with more conservative methods. If we have more information available, if we have more documents, if we carry out more on-site investigation and testing, then we can be in knowledge level 2 or 3. And in this case, we can use any method: linear, elastic, or nonlinear, static or dynamic analysis. Also, from this table, depending on the knowledge level, we can get the so-called confidence factors CF. These factors are usually applied to material properties. When we calculate strength of the members in terms of their capacity, we use these factors to reduce the average values of the material properties. And you can see that these confidence factors decrease from 1.35 to 1.0 as the knowledge level increases. But these factors are also used to increase the mean strength values when we are calculating the strength of ductile elements to find the forces transferred to brittle elements in a framework of the capacity design type. Now, how do we obtain this information? We're already saying that we, first of all, try to find any document available about the building, so we can carry out an historical analysis and some document investigation, looking for original drawings, permits, whatever we can find in public offices, in designer offices, wherever we can find information about the building. We may also try to investigate the history of the building in terms of construction process, modifications that have occurred over time, trying to understand if the materials are consistent throughout the building, or there are additions, there are modifications with new or different materials compared to the original ones. We may also need to refer to historical practices and also look for older codes, if there were codes at the time of construction, because this may guide us in understanding how the structure was built. And finally, we also want to find information about any possible damaging event that the building may have underwent, and these events may have created some weaknesses, or they have induced modifications, retrofits, whatever in the past. Then, as I was saying, we will have to carry out on-site investigations, inspection of details, material testing, and the Eurocode provides us another table which guides us on the amount of elements that need to be investigated in order to reach these limited, extended, or comprehensive levels of inspection and testing. And finally, in terms of material properties, it's always the case to carry out some non-destructive and destructive tests on the building, different amount depending on the knowledge level that we want to reach. And for this, we can use, for example, for masonry structures, flat jack tests, shove tests. We may even take samples of masonry, take them in the lab where we can perform direct shear tests on triplets. So there are quite some different destructive techniques that can be used, and they can be combined with non-destructive methods, because we need to calibrate these non-destructive methods with the results of the destructive tests. But now we have a problem. We cannot test the material everywhere in a structure, and especially when we talk about historical buildings that may have underwent some modifications over time, where materials can be different depending on where we are. Well, we may not be able to investigate all different types of materials. Or we may be selecting a region of the building where material properties are higher or lower than somewhere else. So how can we deal with this? Well, we'll see that the Eurocode doesn't tell us much. It says that we can refer to other sources of information, but it doesn't specify which ones. With the Italian code, the so-called NTC 2018, we find some guidelines on what reference values to use to integrate the results of on-site testing. Another little problem that we find in Eurocode 8 is related to the application of confidence factor and partial factors gamma m to the material properties. Again, we can look for some guidance in the Italian code also for this aspect. Why the Italian code? Well, the Italian code stems from the Eurocode 8, and so it's somehow compatible with the framework proposed by Eurocode. However, differently from the Eurocode, it has been widely applied in practice since 2003, with further modification. The first edition of this code, of these guidelines, was in 2003. It was modified in 2005, then implemented in the full building code in 2008, and revised in 2018. Because over these years it has been used by practitioners, so some inconsistencies or some issues have been found out and solved. So this document can be considered quite useful to find help where the Eurocode doesn't specify very well what to do. So in the NTC 2018, we can find a table with material property ranges. It's important to consider these as ranges. We have a minimum and a maximum values for different properties: compressive strength, shear strength, elastic modulus, shear modulus, for different types of masonry, starting from irregular rubble stone masonry, going all the way to more modern and more organized masonry textures. Also, in NTC 2018, we can find a table with coefficients that can be applied to the aforementioned ranges of properties to increase those values depending on particularly favorable existing conditions, and these are the values within the red rectangle, or improvements due to strengthening interventions. And these are the values within the blue rectangle here in the slide. Again, each line corresponds to different masonry typologies. And the code specifies if these coefficients can be applied to strength, to elastic modulus, the property that can be modified depending on the favorable condition or the strengthening intervention. Again, looking at these tabulated values, the Italian code says that if we are in the lower knowledge level, KL1, we need to take from these tables the minimum strength values and the mean elastic moduli values. And the strength values shall be reduced by a confidence factor of 1.35 as in the Eurocode. In knowledge level 2, instead, we take the mean tabulated strength values and elastic moduli. And the confidence factor reduces to 1.2 as in the Eurocode. Finally, if we are in knowledge level KL3, we can combine the mean tabulated strength values and elastic moduli with those determined from on-site testing. And we perform a so-called Bayesian update procedure. We will see this better in the next webinar of this series, where these aspects will be treated more in depth, showing how to perform this procedure. Now, this is not yet in the Eurocode, in the current edition of the Eurocode, but something similar to what is in the Italian NTC 2018 will be included in the upcoming edition of Eurocode. So you will find in the new edition something similar to what will be presented to you based on the existing Italian code. Also, the tabulated values, also these reference properties will be somehow included in the new Eurocode version. Now, I was saying in the current edition of Eurocode 8, Part 3, there are some issues related to the application of the partial factors, gamma m. Now, again, looking at the Italian code, what I would suggest to do is, for linear elastic analysis, apply to the material strength a gamma m factor equal to 2.0. If we perform non-linear analysis instead, we can use a gamma m factor equal to 1.0 for material strength. Usually, according to both Eurocode 8 and NTC 2018, we should reduce the elastic moduli values by 50% to account for cracked section conditions. The last aspect that I want to mention about knowledge of the building is in reality what performance requirements we have to expect and we have to ask to our building. So what are the limit states that we have to consider? The Eurocode for existing buildings, so Part 3, mentions 3 limit states, 2 ultimate limit states, near collapse and significant damage, and 1 serviceability limit state, damage limitation. And consider that the significant damage limit state is very close to what is considered a no collapse limit state in Part 1 of Eurocode 8, the one for new construction. In the Italian code, there is also a 4th limit state, another serviceability limit state, which is full operationality, which is not included in Eurocode. Now, EC8 refers to national annexes or other national documentation for the selection of the return periods to be associated to each limit state. And also, it refers to these documents to select which limit states should be considered in the analysis. For example, if we follow NTC 2018, for most buildings, we can only refer to 1 ultimate limit state, either near collapse or significant damage. We can just verify, just check one of these. Only for strategical buildings, we need also to consider serviceability conditions. Now, let's move to the next ingredient of the framework, which is the analysis for local mechanisms. Let's start from this video of a shake table test of a masonry building that was performed at the UCenter laboratory a few years ago. If you look at the yellow circles, you will see that the facade excited out of plane of the building is trying to overturn out of plane, developing a so-called local mechanism. This building was not retrofitted in any way. There were no restraints to that facade, and you can see that a mechanism of this type developed at a level of PGA equal to 0.4 G using the 1979 Montenegro earthquake. What are these local mechanisms? Well, these are failure modes that are related to loss of equilibrium of portions of masonry, related to overturning out of plane of these portions of masonry, leading to partial or total collapses. And usually they are due to out of plane actions that are accelerations acting perpendicularly to the wall panels. These local mechanisms are usually adversely affected by the quality of masonry. For example, if we have rubble stone masonry with very poor mortar, or with round stones, with masonry leaves poorly connected with each other, with loose filling between the leaves, all these conditions may lead to the development of local mechanisms, starting from buckling of masonry leaves and loose of infill to overall overturning of these walls. Also, the thrusts coming from roof beams, from arches and bolts may have an adverse effect on this local mechanism. They may push outwards the walls. And also irregularities in plan and in elevation may cause the activation of such mechanisms. Finally, pounding between poorly connected floor or roof diaphragms and walls can also lead to the development of this local overturning response. Instead, we can find favorable conditions when we have good interlocking between intersecting walls. You see here on the left-hand side, we have a case of weak interlock between the perpendicular walls. And in this case, as shown in the photo, you can see that one of these walls is detaching from the rest of the building in an overturning mechanism. Instead, if we have good, strong interlock between the intersecting wall, as in the right-hand side case, we can see that for the wall to overturn out of plane, it has to engage a wedge of the intersecting wall. And if the intersecting wall is supporting a floor system, for example, the weight of the floor may help balancing the wedge and basically delaying the activation of this out-of-plane mechanism. In general, if we have weak interlock between walls and poor wall-to-diaphragm connections or flexible diaphragms, we may be in the most unfavorable case, where walls can separate from each other and easily overturn out of plane. If we improve the interlock between perpendicular walls, but still connections and stiffness of diaphragms are not so good, we may be in a better situation, but still we may have local mechanisms related to bending of the walls out of plane. Instead, if we are able to improve the connection between intersecting walls and the connections and stiffness of floor diaphragms, we may be in the most desirable case, where we develop a so-called box type behavior for the building, as in the bottom case on the right-hand side of the slide. This is the situation that we would like ideally to have. How do we analyze local mechanisms? Well, the Eurocode 8 part 3 doesn't say anything about this topic. The new edition will, but the current one doesn't say anything. So again, we refer to the Italian code, where we find, like as the most the preferred method of analysis, the so-called kinematic analysis. In this case, the wall responding out of plane is discretized in a series of rigid body forming a single degree of freedom mechanism. These blocks are defined by actual cracks that may form in the development of the mechanisms. And the different blocks that are bound by cracks can rotate and slide rigidly with respect to each other. Simplification, but it's quite powerful. Then what we do is to study so-called load multiplier alpha that represents the ratio between the horizontal seismic forces and the weights of the blocks, and the weights also applied by the floors and other structural members involved in the mechanism. Now, this method is based on the so-called upper bound theorem of limit analysis. What does this mean? It means that the actual mechanism that will develop in a given wall is the one associated with a smaller activation acceleration. So you see here on the right-hand side, I've shown two possible mechanisms for the same wall. In one case, we have overall overturning starting from the first floor. In the other case, we have an out-of-plane bending of the wall. Well, which one of these two will develop? The one that is activated by the smallest acceleration. So this means that in order to know the mechanism that will develop, in theory, we should analyze all possible mechanisms that can be developed in a given wall. This can be, of course, time-consuming, but usually the experience of the engineer will lead to the selection of the most likely mechanisms to be considered in order to reduce the computational burden. Now, kinematic analysis can be of two types, linear or nonlinear. Linear kinematic analysis is the simplest one. It requires only the determination of the multiplier alpha naught that corresponds to the activation of the mechanism, the onset of the mechanism. If you look at the figure, the bottom right of the slide, it's the red dot that says linear kinematic analysis. We find that point, the alpha value that corresponds to onset of the mechanism, nothing more. Then once the mechanism activates, there will be out-of-plane displacement of the wall. And before reaching an unstable condition, this displacement could be quite large. If you want to investigate this behavior after activation of the mechanism up to collapse, which corresponds to displacement DC0, this is the displacement of a control node of the mechanism. Well, if we want to look at what happens between activation and collapse, then we need to perform a nonlinear kinematic analysis. With linear kinematic analysis, we consider acceleration and strength checks at ultimate conditions, while with nonlinear kinematic analysis, we look at the displacement, demand, and capacity of the mechanism. Linear kinematic analysis is more conservative because as long as the mechanism is activated, for us, it means that you're at the limit. Nonlinear kinematic analysis is more generous because a mechanism may activate, but we may be far from collapse after activation. And so we can exploit more the capacity of the structure if we use this type of analysis. How to determine the demand? Well, we have to consider that local mechanisms involving portions of masonry should be considered with their interaction with the overall global structure. There is a dynamic interaction. It's like if we have a multiple degree of freedom system. Look at the figure at the bottom left. M1 represents the first mode mass of the overall structure. M star, red smaller mass, is the one associated with the local mechanism only. And it's like having a two mass system in series. So the response of the small mass depends on its interaction with a big mass. However, if this small mass, the mechanism mass, is significantly smaller compared to the overall mass of the building, then we can make an approximation. We can think of decoupling the two responses, the global response of the building to the ground excitation and the local response of the mechanism, using as input for the local response the global output of the building. So basically we treat the overall building as a filter between the ground and the local mechanism. We can do this again if the mass involved in the local mechanism is quite smaller compared to the overall mass of the structure, especially the first mode mass, because usually we refer to the first mode. If we can make this approximation, we can make use of the so-called floor response spectra to get the input for the mechanism. And an example of flow response spectrum can be found in Eurocode 8, part 1, equation 425. That's for non-structural components, but it can be extended to this type of analysis. In the new edition of Eurocode 8, we will find something more refined than what we have in the current version. And also in the NTC 2018, we find a more refined approach to determine the floor response spectra. How can we improve the local response of the structure? Well, there are several retrofit solutions that can be adopted. First of all is improving the masonry quality. In this case, we want to delay disgregation of the masonry, or we want to increase the out-of-plane flexural strength of the masonry. Some techniques involve joint repointing. If the mortar is bad, we can replace part of the mortar joints with new, better mortar. We may make use of grout injections. These are appropriate if we have a loose filling between the two masonry leaves. So we may want to give some consistency to this filling by injecting grout. If the masonry is damaged, we may want to replace portions of damaged masonry with new masonry, with the so-called masonry stitching technique. Or we may want to adopt some reinforced repointing across existing cracks. If we want to improve the flexural response out of plane, we may add vertical reinforcement in slots within the masonry walls. And if we want to prevent separation between masonry leaves, we can use reinforced injections through the thickness of the wall, engaging the two exterior leaves. If we want to improve connections between walls and diaphragms instead, we have other techniques that can be adopted. Again, reinforced injections can be used at corners, at intersections, to improve the interlock between intersecting walls. We may use steel plates to connect diaphragms to masonry walls, and we can build interior, exterior roof ring beams with different materials, steel profiles, composites, steel and timber profiles. And these are all techniques, again, able to improve the connections between the diaphragms and the vertical walls. We can also use post-tension tie rods, which, compared to the other techniques, not only improve the connection, but also confer some kind of self-centering behavior to the response of the building. Now, if we don't have problems with local mechanisms that are usually responsible for many cases of collapses in masonry buildings, then we can start thinking about the global response of the structure. And let's look at again an experiment. This is a building similar to the one that we have seen before, but in this case we have a concrete ring beam at the roof and we have stiffened the diaphragms. See, at the same level of PGA, same input, there is nothing, no visible damage from these videos. Same level of input, very similar building, but with improved connections and increased stiffened diaphragm. So we go to 0.6 G of PGA. 50% higher, and look at the bottom right. You see diagonal shear cracks forming in that pier. This is now an in-plane failure mechanism. No out-of-plane overturning of any portions of the walls. We have only in-plane shear failure of that pier. So in this case, we can take more advantage of the strength associated with our masonry walls. Now, when we talk about global response, so we are thinking about in-plane response of masonry walls and also of floor and roof diaphragms. Masonry walls typically consist of vertical piers, horizontal spandrels that meet at nodal regions. Floor roof diaphragms can be made of timber or other construction techniques, can be steel elements with masonry blocks, can be concrete overlay if the construction is more modern, or we may have vaults if we are talking about more historical buildings. So different systems that provide horizontal connection between the walls. If we want to be able to consider the global response of the building, as I was saying, we need to have prevented, or mostly prevented, the out-of-plane mechanisms of the walls, so that we can develop in-plane failure mechanisms of piers and spandrels. If all spandrels fail within a facade, we can say that we are developing a spandrel mechanism, while if at a given story all piers are failing, we talk about a soft story mechanism. If you look at the photo, the bottom right of the slide, you will see an example. This building was in Amatrice. It was involved in the 2016 earthquake. And you can see that in this building, all spandrels and piers have responded in shear. We have taken advantage of the strength of all elements in this wall, where the out-of-plane mechanisms were prevented by grouted injections at wall intersection and by steel ties. So in this case, the full strength of the building was used during the earthquake. And in fact, it didn't collapse. It was severely damaged, and in the end, it was demolished, but it didn't collapse. Now, in the Eurocode, we find some criteria related to strength of piers and spandrels. Typically, at the ends of the elements, we can develop cracks perpendicular to the axis of the element related to flexural response. Over these horizontal cracks in the piers, vertical cracks in the spandrels, we may develop sometimes some shear sliding. Another mechanism that can develop is diagonal shear cracking. This usually happens within the panel, pier or spandrel. And depending on the type of masonry and on the strength of the joint, we may have stair-step cracks within weak joints, or cracks cutting through the masonry units if we have strong joints compared to the unit strength, or if we have irregular masonry. Now, in the Eurocode, we find criteria related to flexural response, flexural strength, and shear sliding strength. We don't find anything about diagonal shear cracking, but we can find information about this criterion in the NTC 2018 code. In any case, varying the axial force acting on the element, any of these criteria will provide a different strength value, flexural or shear strength. So varying the axial stress on the element, one or the other criterion may control the strength. And we can build an interaction diagram considering these different criteria and taking for different values of axial stress the minimum of the different criteria. And this will be the criterion controlling the response. In terms of modeling of the walls, we can either use 3D finite elements, but this required quite detailed knowledge of the material, and it's quite a time-consuming analysis. Or in most cases in practice, we use a so-called equivalent frame approach, where we make use of macro elements and rigid nodes. So you can see we can identify spandrel elements, pier elements, and rigid nodes. And then we can build our equivalent frame. And in the literature, we can find criteria on how to define the dimensions and the boundaries between the different components of the equivalent frame. Now, this is easy if the wall has regular openings. If openings are irregularly distributed, things become a little bit more complicated. And one of our webinars will be dedicated to how to tackle this particular situation of irregular opening distribution. We also need to model the diaphragms, the horizontal diaphragms connecting the different walls. And usually we have three different cases. First case is infinitely rigid diaphragms. This is the case when we have, for example, a concrete overlay well connected to timber or steel joist. And this rigid diaphragms allow for a redistribution of the story shears based on the relative stiffness or strength and the in-plane position of the piers and the walls. Instead, if the diaphragm is infinitely flexible, it cannot redistribute story shears between walls and piers. And in this case, it is advisable to analyze each wall independently, considering its tributary mass. And this tributary mass will produce the excitation on that individual wall. Finally, the most common case, of course, is intermediate between these two. We have diaphragms of finite stiffness. In this case, we need to evaluate the stiffness based on the construction technique that we have in our situation, and we can use, for example, orthotropic membranes. This is what the program Tremuri, for example, does. And the two axial stiffnesses and the shear stiffness of the orthotropic membrane is calibrated based on the properties, of the actual properties of the physical floor or roof system. The analysis can be based on linear approaches, and in this case, we have to perform strength or deformation checks on the elements of the building. This is, for example, I'm showing here the case of linear dynamic analysis, where we superpose the different modal responses, but even simpler is the case of equivalent lateral force analysis, which is the linear static analysis, which is very conservative usually for masonry buildings. And depending on whether we are using the full elastic spectrum or we are applying the behavior factor Q, we may have to check deformations of the elements or strength of the elements. However, for masonry structures, it's better to use a nonlinear method of analysis for the global response. And in this case, we check displacements in terms of global building response. This is more advisable because it's a little bit less conservative, and it is more representative of the actual response of the building. So it's not limited to an elastic analysis, but it accounts for the development of nonlinearities, of failure of some elements, which may not preclude the capacity of the building of resisting vertical loads and still resist the part of the horizontal loads. We can have, again, static or dynamic analysis, also in case of nonlinear analysis. In the case of static analysis, we perform a pushover analysis in each principal direction of the building. We obtain a capacity curve in terms of base shear and displacement of a control node at the roof level. And we compare this capacity curve basically with an inelastic spectral displacement demand. So we have to transform elastic design spectra in inelastic spectra according to the Eurocode formulation. We will see how to do this in one of our webinars. If we perform nonlinear dynamic analysis, what is the difference? The difference is actually the calculation of the demand, because from the nonlinear dynamic analysis, we obtain directly from the analysis explicitly the displacement demand. And again, we can compare this displacement demand from the nonlinear dynamic analysis with the static capacity curve obtained from a pushover analysis. So the difference between the two methods is on how to calculate the displacement demand. In any case, we have to perform pushover analysis to obtain static capacity curves. In this case, when we model the elements, the deformation capacities of the element depend on the failure mode, shear or flexure, while the strength of the elements are calculated applying a gamma n factor equal to 1.0, as we were saying earlier. This is an example of a building here in Pavia. It is the botanical garden, and you can see some photos and a floor plan of the building and the equivalent frame model obtained from this same building. Now, the model was subjected to a nonlinear pushover analysis. Here you can see at the top right the capacity curve in black, and then in red the bilinear approximation. We'll talk about this in one of the next webinars. We define failure in this case when the black curve drops by 20% from the maximum base shear achieved in that direction, and this corresponds in this case to failure of the wall highlighted within the red circle in the model. You see, it's not the full facade, which is still in decent conditions. We have reached shear strength, but not the maximum available deformation, except for one element in the main facade. However, in this shorter wall, you see that the elements, the main elements, have completely failed. And in this case, this defined the ultimate capacity of the structure. Again, the 20% drop from the maximum strength. The demand comes from the design spectra. In this case, we consider the near collapse situation. The associated spectrum, according to the Italian code, has a return period of 2,475 years. It's the red one in the figure, and it gives that displacement demand shown on the pushover curve. You see that the displacement demand is smaller than the ultimate displacement capacity, so the building is verified for the seismic input of the region. But again, we'll talk about this nonlinear static analysis better in one of the next seminars of this series. How to improve the in-plane response? Well, first of all, we can try to improve the masonry quality. The techniques are the same that you have already discussed in terms of local mechanism. In this case, we want to increase the in-plane strength, but the methods are exactly the same. We can also have other techniques related to jacketing with reinforced plaster or fabric reinforced cementitious matrices, and these are applied, of course, to the surface of the masonry. We also use FRPs, fiber reinforced polymers. In this case, we may have some compatibility issues with the historical masonry substrates. We may also improve the stiffness and strength of the diaphragms, and there are several techniques depending on the type of diaphragm. For example, for timber diaphragms, we can add some additional timber overlays. We can increase the number of nails. We can add steel or composite strips or braces. We can add plywood or even concrete overlays. Different solutions depending on the objective. For vaults, again, we can add concrete overlays, we can apply FRCMs, we can apply FRPs, again, to improve the in-plane stiffness of these elements. Now, with this, I have concluded my presentation.